Hello there, welcome back. In our last video we discussed about relative extrema, and we defined how we define a relative maximum and a relative minimum in multivariable, and we defined how we can find a critical point, and we compared it to what we did last year in single variable calculus. And then we went on for a couple of examples how we can find critical points. And in this video we're going to discuss how we can determine if those critical points are relative extrema. In other words, the point that we found here, this 1, 3, will this be a relative maximum or a relative minimum? And to do this, we can't use the first derivative test that we used last year, our sign charts. It's too complicated in multivariable. So what we're going to use is the second derivative test. And we saw this last year in single variable calculus. The second derivative test says if a function is concave up with the second derivative positive, the function is concave up. We have a relative minimum. If the function was the second derivative negative, the function was concave down, and we had a relative maximum. The idea is the same in multivariable as well, except for it's not as easy to take those second derivatives, and the test is not necessarily easy. So we are given this formula right here. Now this formula is way too complicated for us to derive. It's way above our pay grade. We're not ready for that quite just yet, so we're not going to worry about this right now. But we can apply it. So suppose we have a critical number and the second order partials are continuous. We can define the second derivative test, that's what this is. This is that second derivative test as the following. D, the second derivative, is the product of the second partials of x multiplied by the second partials of y minus the partials of xy squared. So notice we're looking at a second derivative. Remember, yx, xy doesn't matter. That was Clairaut's theorem right there. And this formula right here will help us determine if we have a relative maximum or minimum, given by these conditions. If D is positive, and the second partial of x is also partial, then we have a relative minimum. Now what this is saying is, and we're going to show this in another video, that if fxx and fyy are both, in this case, positive, if they're both positive. Now if you think of the second derivative, what this is kind of saying is that, okay, if they're both positive, then my second derivative in the x direction is concave up, and the second derivative in my y direction is also concave up. And if you kind of compare them, we can get something like this, and going backwards, up, like so, we would get a relative minimum at our critical point right there. So if both are positive, then both are concave up. Both directions are concave up. And we have a relative minimum. If we look at the agoid of mathematics right here, here's the agoid of mathematics. Here is a minimum value right down here. So what's saying is, if I look in the one direction like this way, I know that's concave up. Remember, think about it like as a trace. I'm tracing along just the x direction. Here is concave up. I have a minimum value down there. Well, if I wrote in the y direction also, we have a parabola that is concave up. And so since I'm concave up here, I'm concave up in this direction, we have a relative minimum. Likewise, what if I want to get a relative maximum? Well, in this case right here, my second derivative partial with respect to x is less than 0. And D is also still greater than 0. So kind of the same thing. In this case, both the partial with respect to x and the partial with respect to y are concave down. So we would have, like last year, concave down, we would have a relative maximum at that point. Now, if D is less than 0, we have what's called a saddle point. We've talked about this before. What's kind of like here saying that either fxy and fyy will have to be opposite signs. In other words, one is concave up and one is concave down. And in the middle, we have a saddle. So imagine like we have something like this, right? Just let me see here. So imagine we have function concave up, and then we have something concave down. Where they meet, we have a saddle, and that's what's happening right here. And like in BC last year, what if d is 0? What if my second derivative is 0? Well, it could be a maximum, it could be a minimum, it could be a saddle. We don't know yet, so we won't be able to solve those just yet with the techniques that we have right now. All right, so I'm going to take a pause right here. You can go into the next video. Is just going to be a quick little proof of why we only have to look at the second partials of x for relative minimum or maximum. And we're going to talk about how we know it's going to be a saddle point as well if they're opposite signs. So go on to the next video if you like, and I'll see you then. Okay?